Thanks for the introduction. I guess it's a nice theme today. I don't know if it was on purpose, but I guess mine is a bit more general, but I also focus on my study systems, obviously. Yeah, so like for the general introduction, so we tend to, when we look at a disease in wild species, to usually target on one, focus on one target species. So for instance, in my case, I work a lot in Subantarctica. So it's always about penguins or albatrosses, and we don't really care about the rest. But obviously those species evolve with other species in their environment, and they can play different roles. So we can have one species that is heavily affected by a disease, but we can have other species that help move the pathogen around, or some that are helping maintaining the pathogen in the system. And usually that different interest is driven by the fact that some species might be more emblematic or might have a conservation concern on them and things like that. So it's not coming out of nowhere, but it's still really preventing the way we can understand and control infectious disease when we want to control them. And it's important to understand the role that the different species play, because that helps us design targeted interventions. So for instance, if we keep I don't know, vaccinating all the albatrosses, but then there is another species that keeps transmitting a pathogen to the albatrosses, then we might have to vaccinate them forever. While if we targeted the maintenance species, we might have a way more efficient solution to our problem. So the interventions I have in mind are, for instance, vaccination that I mentioned, but there's also one that is like the ideal scenario that is almost never achieved, but is removing the reservoir species when we can. So the species that are responsible for the maintenance and the spread. And there's one case where actually we can do it quite easily, and it's done even if it's not for the purpose of disease control. It's removing rodents, and particularly on islands where we have seabirds. So that's one of the reasons why I work so much on Oceanic islands. So I'm gonna go over two examples. One more like a nice story with data and stuff, and one more like speculation of things that I think you guys might be interested in and we could talk about. So the first one is avian cholera on some islands in the southern Indian Ocean. So this is a typical subantarctic island where we have big cliffs with lots of seabirds. And in that specific island, Amsterdam Island in the southern Indian Ocean, you can very often see that kind of scenario, that kind of pictures where we have a parent on its dead chick. And these dead chicks, after several years of investigations, we understood that there were massive mortality events affecting the chicks, and they were causing almost all of them to die several years in a row, and that has been lasting since the mid-80s. And we found out that the avian cholera, so Pastorella multocida, the bacteria causing avian cholera, was very likely responsible for those mortality events. So you can see the prevalence of Pastorella multocida increasing over the breeding season as the survival of the chicks drops. We did isolate the bacteria from dead birds, so that was already a good evidence. We found some lesions that are characteristic of septicemia in the dead birds. So again, and then the nail in the coffin was that when you vaccinate the chicks against Pastorella multocida, you considerably increase survival. So now we're pretty confident Pastorella multocida is the culprit, at least for part of the mortality events. And this is affecting the main species we have on this island, the yellow-nosed albatross, but also other species that are breeding around, so the sooty albatross or northern rockeper penguins. It's not affecting so much these other species that is nesting a bit higher on the island. So it's messy, but like the message you get from this plot is that we have recurrent crashes in breeding success. And that's causing a decline in those species that are affected by the outbreaks. So there's a conservation concern here. So the nature reserve came to us, these ecologists, saying, do something. So you might think we have a vaccine, so the problem is solved, we can vaccinate the birds. But there are 20,000 pairs of albatrosses there. So I don't think anyone wants to, spend their whole life get vaccinated one bird after the other. So we thought, let's look for actually where the bacteria are coming from. Why does it keep coming back every year? And why that's a big question is, I don't know if any of you is familiar with seabirds, but seabirds are very seasonal, especially in those environments where especially in those environments where we have strong seasons. So in subantarctica, strong summers, strong winters. And so if you look at how many birds are on the island, in summer it's full of birds, and in winter there's no birds. So that's like just the end of the breeding season. And if you come back 2 weeks later, there's just no one on the island. So it means that every year the birds are coming back and they get sick again. So is it because they keep bringing the pathogen with them that they get from somewhere else? We didn't find any evidence of that, notably because when we do genetic of the pathogen, it looks to be the same more or less every year. Maybe there's sustained at sea transmission. So same, we didn't find any evidence of that. The bird seems not infected when they come back from their winter migration at sea. Chronic carriage, same, no evidence of that for the same reason. Birds are healthy when they come back. Maybe an environmental reservoir. So it's very hard, obviously, to rule that out completely, but we looked for it. We never found any evidence, so maybe, but not sure. But then there's one last thing that came to our mind quite late, but it's that maybe there are repeated spillovers from another species on the island. And I told you about the birds. The birds that we know are on the island, but there's another species that I haven't mentioned, and that's introduced rats. We also have mice. And so eventually we were wondering, maybe they are carrying the pathogen and transmitting it to the birds, and they are the ones playing as reservoir in the system. So for transmission to happen, we need two things. First, we need contact. So we looked if there were contacts. So that's a pile of rats eating a dead albatross. So ideal setup for the rats to get exposed to Pasteurella miltocida. And that's a rat feeding on a live albatross chick. So that's an opportunity for the rats to then transmit the pathogen to the chick. And I mean, it's like kind of like what Sabrina was saying, like the species have evolved with no predator, no terrestrial predator, so they don't know how to react when they're getting bitten by a rat. And it's happening quite often. You find lots of chicks with wounds on the neck or on the legs, suggesting that they've been attacked by something that just took a little piece and went away. So they could transmit the pathogen in that condition. And then we looked if they were actually carrying the pathogen. So that's a map of the island. And you can see at the north, we have the scientific station where people live. In the middle, we have that flat plateau with not much avian cholera happening in the birds. And in the south, we have the big dense cliffs with lots of seabirds. So the yellow points are rats that were captured and PCR negative for Pasteurella, and the red dots are PCR positive, so supposedly infected. And you can see that big cluster where there are lots of birds. So that's evidence that it's going from the birds to the rats. And you can see it's very structured in space. So that's on the southwest here, it's the hut where we live, and there's almost no positive rats. And if you just walk like 10 minutes up in the cliff, you have almost all the rats are carrying the bacteria. Then we looked at the same thing in winter. And again, in winter, there's no bird on the island, and the rats are still carrying the bacteria. And we find them a bit more scattered, so maybe they move during winter, but anyway, they're still carrying the bacteria, so that could be the reason why when the birds are coming back every summer for breeding, then they interact with the rats and they get infected again. And then, like, to get a complete picture of what's happening, we also looked at scavenger species that are living on the island. So here it's skuas. You can imagine it's like a brown seagull. And so they feed on both dead birds, dead rats, they hunt the rats. So they're very likely to be also exposed. And so the kind of thing we do to understand the role they can play is putting GPS loggers on them to see if they could help move the bacteria once it's moved from the rats to the birds. And you can see that's just a few individuals within one day that they go all over the islands where we have seabirds nesting. So imagine if you have one cluster somewhere, then they can potentially, eat a dead bird or a dead rat and then move the pathogen around. So that's kind of like the epidemiological network we built for Pasteurella miltocida on our island. So we have the birds, the albatross and penguins being affected. We have the skuas moving in around, and we have the rats acting as maintenance hosts and potentially also helping with transmission by moving between nests. And so why I'm saying that islands are good open sky laboratories is because we can also treat them as giant petri dishes. So we have those relatively close units. We don't have much introduction from the outside. So for instance, the birds are migrating at sea, but they don't go inland to other places where they could interact with other birds during winter. We can treat them. So for instance, remove rats. And we can also compare islands, for instance, if we have islands with or without rats, or islands where we add rats and remove them versus islands where we kept the rats. And so on Amsterdam Island, it's kind of like, it's a coincidence, but the nature reserve was planning to remove the rats anyway. So it's happening at the moment. So they are removing the rats. Actually, they're going to start this June. So we're pretty excited because we're going to be able to see if removing the rats also has an impact on the dynamic of Pasteur Mutocida. And hopefully if it leads to the local extinction of the pathogen with the removal of the suspected reservoir species. And so you might say, okay, they're very lucky. They found like, a system where rats were a reservoir and potentially reservoir, and they're being removed for a completely independent reason. But actually introduced rodents are being removed from islands quite often. So for instance, that's projects that are led by island conservation just over the last few years. So you can see it's lots of islands all over big chunk of the world. There are also big projects like, for instance, New Zealand has the ambition of becoming predator-free by 2050. So it means lots of islands where they are going to remove cats, rats, mice, and other exotic predator species. And so, when we study reservoir species for infectious disease, we always say, okay, the gold standard is to remove the species and see if the pathogen survives the removal of the species. And there are all those little experiments that are being conducted, but very often there is no epidemiological data that are being collected because those removal programs are being conducted for other reasons. So usually we are mostly concerned about predation or habitat destruction, but not really about a role as in an epidemiological network. But we can do lots of things, even if we don't look at a specific pathogen. So for instance, in our case, we are looking at Pasteur Mutocida, but we're also looking at other pathogens that can be rodent or cat-borne. So leptospirosis and Toxoplasma gondii, for instance, in my case. So I do those studies mostly in the Falkland Islands, which are in the southern Atlantic Ocean. And we also use some kind of like surrogate microbes that can inform us on what will happen with the pathogen. So for instance, looking at microbial communities. So for that, this is a whole, I'm collecting lots of samples, but I don't have the expertise to do kind of like pathogen community study. So if anyone is interested on collaborating on those kind of questions, I'm keen. And we're also looking at things like presence of antimicrobial resistance in wildlife, depending on the occurrence of farming and also introduced species. So that was the one nice story. Now I just want to throw on the table the more like speculative, maybe it's interesting, maybe not kind of story. And it's looking at avian influenza. So I'm sure you're all aware of the highly pathogenic avian influenza pandemic that's happening. So lots of chicken and other poultry dying everywhere. And also lots of wildlife. And within wildlife, seabirds have been really hammered by the virus. So for instance, that's a map of Scotland from last year where you can see more or less anywhere there's a seabird colony, there were dead birds. Some species were more affected than others, but you could see like very dramatic pictures like those ones with lots of dead birds everywhere. And so that was in Scotland, but over the last year, the virus has spread in America, notably in South America. So in the community, the seabird community, we all got very concerned about what could happen with Antarctica, because we obviously have big seabird communities and with species of that are very emblematic, despite and in addition to the like biodiversity questions. And it's actually right now, like since last October, the virus is making its way towards Antarctica. So we had the first cases in South Georgia, so that's where we have the 21. A few cases in the Falklands, where we are number 4, and now we have suspected cases on the peninsula, on island around the Antarctic Peninsula, so number 2. And what is very interesting with those cases is that most of them are actually in mammals, in elephant seals, and there are very rare cases in seabirds, and almost all of the seabirds are actually scavenger species. So the skuas I showed you before, giant petrels, gulls, and species like that. And that's surprising because when you Google South Georgia, for instance, you always have those pictures of elephant seals and penguins sharing the coastlines. So my question is, if we have the virus that is supposedly so transmissible between seabirds and present in marine mammals that are sharing habitat with the seabirds, you would expect all those penguins to eventually catch it and die, because we've seen penguins dying, for instance, in South America. So what I'm wondering what's happening is on what strain was actually introduced to those islands. So for instance, in South Georgia. So far, what we've been considering is that birds were moving the virus between sites, and eventually you will have some spillovers to mammals. So for instance, in the US, we've heard about a few foxes, a few bears here and there. But when you look at like South America or in Scotland, where you have lots of coastline, we had some spillovers to seals, and then seal to seal, or highly suspected seal to seal transmission. So potentially a strain that got adapted to mammals. But I wonder if in subantarctica right now, what we're having might not be strains from mammals that spilled over from South America to those subantarctic islands and are actually struggling to transmit between birds. So they reach the scavenger that are spending their days eating dead seals, but they're not transmitting afterwards to other birds. And in that case, I think that would be super interesting to look at, because we could see, we can already know what it does when a bird virus reach a mammal community, but in that specific system, we would have the reverse situation. So see if the virus, for instance, can adapt back to the birds or things like that. And there are lots of logistical challenges into getting sequences from those viruses, but hopefully we will get a few, and we can address questions like, first, confirm the transmission chain, whether it's coming from mammals or from birds. See if there is what are the signs actually for adaptation to mammals in a place where we do have lots of opportunities for mammal to mammal transmission, and see if we can have readaptation to bird in the other world. And yeah, so that's my conclusion. And obviously, for the sake of time, I didn't introduce everyone who worked on that project, but it involved lots of collaborators for the different projects. Taking any question.